Wonderful. Well, welcome everyone. Thank you so much for joining us today for the Grasp on Robotics series. As a quick reminder, this and previously recorded talks can be found on our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen. These will be answered by the Q&A panel at the end of the talk. Now, I'd like to introduce our Grasp faculty host for today's talk, Dr. Vijay Kumar, Dean of the School of Engineering here at the University of Pennsylvania. Thank you so much. Have a wonderful day.
Thank you, Gabby. Thank you, Mark. Good morning, everyone. It's a real pleasure to introduce to you today Dr. Timothy Chung. Dr. Chung did his undergraduate work at Cornell University and then his graduate work at Caltech. I've known him since he was a graduate student at Caltech. And he's done some really interesting work during his doctoral work on active target tracking, on sensor selection and decentralized control and sensing. After that work, he joined the Naval Postgraduate School, where he did a number of things, but most notably, he was responsible for what I believe at that time was the largest demonstration of fixed-wing aircrafts, showcasing really a swarm of tactical UAVs. A very impressive work that he did at NPS, and he did a bunch of other things. But we have invited him here today to tell us what the future of swarming technology is, and as he sees it in his present role at DARPA, where he serves as a program manager in the TTO, which stands for, and I'm desperately looking, Tactical Technology Office. Thank you. He joined DARPA in February 2016, and his interests now have gone beyond UAVs to ground vehicles, to collaborative autonomy. And of course, many of you were involved in the SubT project, which was also something that was a brainchild of Dr. Chung. Without further ado, I'm going to turn it over to Tim Chung. Tim, take it away.
Great, thank you, Vijay, and thank you, everyone. It's a pleasure to be here with the Grasp Lab. I feel like every time, once upon a time, we went to ICRA, I would be hanging around a bunch of Grasp attendees from Penn, and they would just kind of adopt me for the dinner outings or whatnot. So it's always been a great second home, I'd say, from that perspective. And let me go ahead and share my screen here. Let me just get a confirmation. You can see the presentation. All right, great. Yeah, so it is absolutely a pleasure to be here, and I'll first highlight a number of ways in which the experience at DARPA has been something that's been pretty positive for me, and how it highlights the trajectory of some of the work that I'll be presenting today, and hopefully can share some of that experience and enthusiasm with you today. All right, so I think just to start things off is, as Vijay mentioned, I'm a program manager in that Tactical Technology Office. For those of you who aren't familiar with what DARPA is, I wanted to just share. DARPA's kind of core at its heart is the notion of technological surprise. And in particular, it's really interested in creating that technological surprise. What do we mean by that? It's really thinking through not just what's the problem of today, not the problem of tomorrow, but the problem after that and the problem after that, and understanding what it means to plant the seeds accordingly to be able to create that technological surprise. And in doing so, that also gives us an opportunity to anticipate where technology is going so that we, the United States and our partners, aren't surprised ourselves. And I think that comes from the legacy of the Sputnik scenario over 60 years ago, and never wanting to be caught surprised again. So DARPA is really focused on this technological surprise. And what that really gives DARPA this mandate to do is think very deeply and broadly and anticipate where technology is going, and oftentimes help guide and drive innovation in particular directions. As Vijay mentioned, I'm part of TTO. So DARPA has these 6 technology offices. They typically focus on basic research and component technologies, but why I really love being in TTO is because it's considered one of these systems offices, What that means is it takes these component tech, the basic foundational research, and has to, by charge, bring it all together, integrate it, and then demonstrate the system working. And I feel like that's descriptive of what we have to do as roboticists and generate that street cred of taking the research that we're trying to advance, but also then demonstrating it. That's kind of how we operate. So TTO feels like a perfect fit for folks like myself and yourselves interested in robotics. But as I said, technology spans the wide gamut, everything from biology to cyber to miniaturization and things of that nature, all the way to understanding how to manage large battle spaces and things of that nature. So again, a lot of different moving parts. I am one of about 100 program managers. So what I'm going to present to you today is about 1% of what DARPA has been doing and keeping busy. But I think out of that cadre of 100 program managers, it's definitely a distinct privilege and opportunity to be at DARPA. And so finally, I wanted to just introduce what we call the Helmer Catechism. This is what's known as the set of Helmer questions that are asked. And the reason I wanted to share this is because if you know these questions, you'll be able to get into the minds of how DARPA operates and thinks when addressing a new topic, defining new programs, evaluating proposals, etc. These sets of questions is going to be asked to any program manager pitching a new program, or any faculty member or researcher trying to seek research funding. And being able to answer these questions are deceptively easy questions to read, but very, very hard questions to nail down your answers. And the reason I showcase this is because I remember as a grad student, my advisor pointed on his bulletin board a printout of these questions as we were going through my dissertation discussions. And little did I know that those were the very Helmer Catechism questions that I'd be facing once again upon my arrival to DARPA. So I encourage you to take a look, and as we're going through this presentation, maybe some of these questions will come out, and of course, see how these questions apply to your questions of interest as well, whether it's for your dissertation, your next proposal, or your next research lab endeavor. Okay. So jumping into it, I've had the privilege and continue to have the privilege of working on a number of programs, and I wanted to share two of them with you today. The underlying theme of the work that I'm interested in is how do we get robots to operate in these real world settings? This is that notion of field robotics, and it's still in some cases quite maturing, but in many other cases, we still have a long ways to go. And the types of environments that I'm particularly interested in are encapsulated with these two programs, offset program called the Offensive Swarm Enabled Tactics Program, and then of course the DARPA Subterranean Challenge. And so one operates in complex urban environments with all the intricacies that you might face in those built up environments. And the other works in complex underground environments, which I'll describe in greater detail here shortly, but predominantly you can already anticipate where some of these difficulties might lie, as well as where some of the commonalities between these two complex environments. So to give you a quick introduction of offset at a glance, what we're trying to do here is discover those technologies that will allow for large-scale teams of air and ground robots operating in support of small unit forces in complex urban settings. So what do I mean by this? Well, the first takeaway is heterogeneity. I have air and ground, so drones and rovers and fixed wing, and they all have to work together in this mission environment. We have small unit forces. That really means you can't have 250 operators, personnel, soldiers, firefighters, whomever, flying or driving these robots. But when we're talking about 250 robots, how do we do that with few humans to be able to manage that and orchestrate the entire large group? And then the complex urban environments, you have the verticality that you might find from the buildings and the superstructure. You have the outdoor and indoor problem. You have lines of sight challenges, both for your sensors, but also for your communications. And also the channelization, as we call it, it restricts maneuver. You just really can't maneuver as freely as you can, as opposed to in a free, obstacle-free environment. So that is the environment that we're interested in. And so imagine the scenario where you want 250 of these air and ground robots, dealer's choice how you want to compose your fleets. I'm operating out of about a square mile, right? So 8 square city blocks for a duration of 4 to 6 hours. And I want to conduct realistic operational mission sets that would bolster human forces that might need to conduct operations in these urban environments. So that's what Offset is about. We'll be focusing predominantly on swarm autonomy and human swarm teaming, recognizing this is just part of a long march towards enabling future swarm capabilities. As an overview of SubT Challenge, here we're leveraging what is a DARPA Grand Challenge model to discover technologies that will deliver this notion of actionable situational awareness, and to do so across diverse underground environments. And so here, the takeaway is we're interested in robotic systems that can be resilient and adaptive to the fact that underground has many different flavors, whether that be human-made tunnels, urban infrastructure and underground environments, and then naturally occurring cave networks. How do you get robotic systems to be able to conquer all of those environments in this way? And I'll describe the construct of the DARPA SubT Challenge in greater detail here shortly. Okay. So starting with Offset, let me introduce, and this is just some video that I'll voice over here of field tests that we conducted back in September, all COVID safe, and happy to report everyone was still safe. But this was out in Washington, and it'll get a glimpse of the lay of the land. This is a typical test site that one could go to. You can see everything from multi-story buildings to sprawled out road networks to challenging curbs and doorways and stairs and things of that nature. We've deployed ground rovers and small drones. And the idea here is the name says offensive. That just simply means that you don't have home field advantage. So the idea here is, how do you deploy these drones and rovers to go and conduct urban missions, for example, gathering information and intelligence, locating where high value individuals might be located within a building, maneuvering into said buildings, being able to then secure and defend a particular area. So we'll have a couple of deployment zones. We'll launch 10, 20, 30, 40 robots at a time per launch zone. They have to kind of maneuver into the city center and conduct their operations as they're going along. Here you just see one of those deployments. And the idea is, how do you leverage, what is the value of a swarm in these settings? So being able to say, hey, I need to know where ingresses and egresses are of these sets of buildings. So the subswarms divvy up amongst themselves to go and scan the sides of walls, scan the rooftops, things of that nature. The ground rovers get to deploy according to the road network that they're able to decipher from overhead maps and such, of course, and they deploy themselves to go and interrogate different buildings, etc. So this was just intended to kind of give you the sense of scale of what we conducted. We did have to waive off on our January field test, of course, due to COVID, but we're excited to go and test again in June. And I think the main idea here is, as I alluded to earlier, this march to swarm capabilities really requires us to think a little bit about how to represent the swarm information and such in a meaningful way. And Offset is elected to do it through this notion of swarm tactics. So really, oftentimes we technologists tend to love to develop algorithms kind of at the bottom up approach, compose those to do meaningful things, and then finally get to try to conduct a mission, but there's still a mismatch there. Whereas what Offset's interested is taking that swarm mission, that's what we call commander's intent, translating commander's intent into these things called swarm tactics, and using that high level kind of top-down approach for thinking about what is required to execute the commander's intent is the name of the game for the Offset program. And so we have two teams, Team Rise, led by Northrop Grumman, and Team CCAST, led by Raytheon BBN. And they both are charged with developing the swarm systems architectures and the supporting infrastructure, whether that be the simulation environments or the test beds to go and test that on. That's their charge. And so we have these kind of two approaches to go and addressing this desired effect of defining swarm tactics and using that to conduct these high-level missions. And so the real takeaway I want to leave y'all with is that given these approaches, we now have built out and continue to expand this repository. We call it the Swarm Tactics Exchange, but think of it as a repo for the code, but also the documentation that leads to how to make use of it, but also how to develop in that space. So describing that a little bit more, here's just a smattering overview of the sets of tactics, these swarm tactics at the high level. The definition we like to use for swarm tactics is it's the thing that the commander intent, when she wants to conduct a mission, will be able to utter, and that is known and understood and processed by the swarm. So you wouldn't say, go to waypoint 42, go to waypoint 43. You would say, surveil building or surveil area. And the swarm and or the subswarm is capable of understanding what that means. That's that translation of commander's intent into swarm tactics. And so we've been growing this repository. This is just a swarm count, swarm tactic count. You'll see it non-monotonic, which is interesting, but a large part of that is because defining what it means to be a swarm tactic, vice some of these lower level primitives and algorithms, causes us to merge, combine, deprecate. And so that's where some of that non-monotonicity comes from. But this perpetual growth of, as we expand the mission sets we're interested in, you can add to the repository of these swarm tactics, and they have a variety of implementations. And the other thing I want to show on the bottom left is how we interact with them. So these scribbles that you're seeing there are actually sketch gestures. You can gesture on a touch screen with the pen, and that's how one invokes said tactic, the associated swarm tactic. On the right, the CCAS team is elected to use virtual reality. So under an HTC Vive headset, there are now these glyphs that can be used to invoke the swarm tactics. And so these are different ways to think about that human swarm interaction piece here as well. So here are a couple of spotlights just to highlight. The top row are those coming out of Team Rise. The bottom two are from Team CCAS, using that sketch interface and the virtual reality interface. And so the idea here is conduct an overhead scan. You might have just designated a wide area. That's kind of the cyan line looking in the upper left. And the agents are working with swarm primitives and algorithms under the hood to go and decompose that environment and create a scan pattern to go and do that. And one drew an O to invoke that tactic, for example. Looking on the bottom, for example, you can specify polygons or designate if you can semantically represent, and I know this is ongoing work there at GRASP, if you can semantically represent environments, or for example, an object or a building, you can point to that building and say, surveil that building, and whether it be air or ground, the agents can go and kind of organize to go and maneuver and conduct that surveillance, gathering imagery or other information as appropriate. So these are the different ways that one might be able to interact with these swarm tactics, and I think that's part of what OFFSET's keenly interested in. So as I mentioned, there are these two approaches, and part of this is because I would argue, we still don't know what the optimal system architecture might be. That includes everything from the interfaces and the middleware. So this is our quest to at least have two reference architectures that now we can understand, at least comparatively, do an A/B comparison of what works and what doesn't work. So in this sense, we have the Team Rise and the Team CCAS coming in. They're charged with kind of developing this library of swarm tactics and implementing them. And I think one of the things that we've learned, and that many of you are familiar with, is that when you're dealing with real world missions, rather than understanding how to solve a task, a single task, as opposed to many tasks that go into that mission, there's a need for composability, and composability of the technical approaches, that is. The main reason for that is, as much as I would love, for example, expected information gain to be the mathematical construct that governs the entirety of the mission, that might not be the case. So I need to be able to stitch together an information gain based primitive, compose that with maybe a barrier function approach, tie that to something that's consensus algorithm driven, and compose that in a way that will allow that commander to realize and execute her intent in that real world mission. I think the second piece here is that if you want to, assuming we don't know the answer up front and we're not just solving and implementing a known solution, you need flexibility because you don't know what you don't know. So we know this in research, but the ideas that might come about don't always fit into a narrow interface specification or interface control document definition. So flexibility in how we think about these architectures is critical as well. And so offset explicitly relies on composable and flexible autonomy in the context of swarm tactics, being able to get mixed together amongst themselves, mixed together with primitives and algorithms to compose them. And one way in which we exercise that is through the use of our third-party developers, if you will. We call them swarm sprinters. And the idea behind this is these swarm sprinters are coming up with novel ideas, much like many of you in your research endeavors, and how they come about implementing those ideas. If there isn't a receptacle in the architecture, then you would miss out on that idea. So having that flexibility to be able to adopt and plug in at a variety of different levels is key to being able to incorporate those new good ideas. And so here's an example. Here's a representation of the 35 swarm sprinter efforts that we've had. Some of them have come in developing these high-level swarm tactics and have been able to develop and implement them that way. But others have really brought in something novel at the algorithmic or the primitives level, and we want to make sure that those are adopted and then perhaps are leveraged to be built upon. And when we say open architecture, we really mean they're open to new ways of solving the problem in terms of pathways to integrating that technology. I think the other exciting thing here is that you see many different organization types, universities, of course, bringing in a lot of that cutting edge new work, but also businesses, small businesses and larger organizations and research labs, all able to kind of work to plug into offset. So here are some examples of what some of these sprinters has done. Specifically, more recently, Michigan Tech is able to imagine a swarm tactic that requires a building scan that is leveraging a synthetic sensor that has see-through wall sensing. And imagine what you could do if you could scan buildings with drones pretty quickly, multiple floors, and generate a rendering of the floor map. And that gets overlaid to your virtual reality interface as shown here. And now I scan over and I can see what the floor plan looks like, which might change how I deploy my assets and which tactical choices I make. The middle scenario with the University of Buffalo, leveraging our simulation capabilities to think about neuroevolutionary machine learning approaches to imagine what happens when there's adversaries trying to oppose these blue swarms coming in. So now we can study how to support that from a machine learning perspective. And then on the right, Johns Hopkins came in thinking about some of the limitations that we find with our multi-rotor platforms like endurance and standoff distance. And so what if we could take advantage of fixed wing aircraft, deploy them from far away, but now they're operating below roofline heights and they're in that urban canyon flying aggressively around, being able to do things like scanning buildings, just like we might have used a quadrotor for. And so this is using, Pixhawk to go and fly aggressive patterns around the environment. And you can expand this to not just things like scanning buildings at different floors, but also imagining things like pursuit evasion and other things that are making use of that post-stall regime of these aircraft. So all of these get fed into the offset architectures, which is pretty cool. And I think that's one of the hallmarks of offset here. Those two integrators, as we call them, RISE and CCAS, they're also responsible for developing swarm simulators. And again, I know this is an interest area for you, and everyone is probably quite aware of this trade-off where we would love to get high numbers of robots simulated because this is a swarm robotics program after all. And so we're interested in the interplay between all of those agents, and in particular, how can we use that simulator to craft and design new swarm tactics? Well, it'd be great if we can play that out. But of course, the farther we get into that high scalability, we drop off in fidelity, and that fidelity, that low fidelity lends itself to challenges when you want to transfer to the real world systems, because there's just a larger hurdle from a transfer of, translation of robot code, for example, to get there. Conversely, you have that high fidelity simulator, but you just can't scale as much. And for a swarm tactics program, that's quite the limiter as well. So what we've done here is basically 3 sims in one, where you're able to basically scale as necessary, depending on what you're interested in doing. Full flight physics, all the way down to agent-based models, and making use of the Unreal or the Unity simulators kind of across the board. And that gives us the flexibility to do things like apply machine learning approaches on the low fidelity, but highly scalable, potentially faster than real time, but also allows us to scale up in fidelity when we're eager and ready to go and deploy in real robots. And I think that's the takeaway for Offset is, how do we speed to fleet? How do we increase the speed to fleet? Because at the end of the day, I want to get these robots out there and flying and driving around. So the benefit from Offset has been these 2 different approaches. They essentially converged on level 1, 2, or 3, or the other one calls it featherweight, lightweight, and heavyweight. They converged on this need simply because the requirement of generating swarm tactics, but the desire to not have to rewrite or port code every time they come up with a new tactic. And so that scalability is now baked into these 2 simulation environments. So here's some screenshots of what we're talking about. We can imagine doing large scale scenario play with, I think that's 200 agents on the upper left executing scenario tactics just to see what that would look like. We can also have a lower, kind of a medium tier sensor model that would allow for us to deploy and see what sensor coverage might look like. The upper row here is Unity based simulation. On the right, upper right is the fact that we can now deploy this simulator across multiple hosts. So multiple computers, laptops, what have you, maybe instances in the cloud, can all work together in a network fashion by virtue of this architecture to go and scale as well. So that scalability shows up there. Faster than real time is definitely desirable. Being able to port in real world models, 3D models of the field test environment, and then do mission rehearsal, even right before pressing the go button to launch. That's a capability that's critically useful for increasing the probability that your field test will be successful. And then also affording the ability to study those kind of environmental interactions with the scenario. So modeling robots going into buildings and having interactions with scenario elements is it's an accelerator to getting the robots in working in the real world. And so all of that is great, but at the end of the day, as I said, we want to get them out there in the real world to really work with these robots. And so I think the takeaway as it pertains to swarm tactics is that there is clearly a dependency between swarm tactics and what you want to do with what you can do with the platforms that you have available. So for an example, we've now have an understanding of, if you really need to amass swarm power, let's say mass, so swarm size, and you need to generate that quickly, so surge strength, there are certain tactics that really benefit from that. But if your agents can't handle it, whether from a deployment or a transition point of view, then you just won't be able to leverage that swarm tactic. And conversely, there might be other swarm tactics that allow for you to kind of ramp up your swarm strength, your swarm power gradually, and build up that way. But then maybe your endurance is limiting and you just won't be able to amass enough because the batteries are dying. So understanding that interplay between swarm power and the associated time derivatives of that, as an example, really plays an impact on swarm tactics. And that's one of the places where the physical testbed helps us craft the swarm tactics accordingly. And then many of us already know this, but COTS hardware changing as quickly as it does really calls for extensibility. Once again, understanding, as you can see, the different types of platforms shown here. Some of these have already gone end of life. Throughout the life of the program, we've seen drones come into market and leave market all within the life of the program already. So understanding what it means to design swarm tactics that aren't tied to hardware, but are more software defined, allows for that extensibility as well. And so, of course, here we have the autonomy stacks that live on each one of these platforms, nested together in their respective offset architectures, demonstrating the incorporation of new sensors, new radios, new platforms as they come online. So here are some just examples of the work that we've continued to do. The middle one, for example, is a really great example of taking work. Mike Rubenstein out of Northwestern had minimalist sensing for swarm agents. He partnered with a larger company that was able to take that research and turn it into a product that we are now mounting on these drones to be able to do bearing and elevation sensing. So taking that research concept and maturing it to the point where we can deploy it on drones. On the bottom right is an example. It's basically a trailer for 80 drones of mixed type with 2 launch and landing decks on top. And it's a robot that launches other robots. It receives robots, charges them, places them in cells. But then now you can call through an API and just launch robots at a time. And so this is another piece that impacted what we do for offset. And so offset really has been exciting for me. As Vijay mentioned, I'm keenly interested in large scale teams, but understanding when and where those large scale teams are useful has been a continued lesson learned for the offset program. I think it's important to kind of understand the role that swarms can play, and understanding the baselines from which you need to have that point of departure. I think there's still a lot of things that we have yet to solve or learn. And I think still solving a lot of the mobility challenges in urban settings is going to be an opportunity for us to elevate where that point of departure and platform capability is. Logistics is always going to be a challenge. And then also the notion of, now that we understand how one might use these systems, can we understand how to defend and secure safely as well. Okay, I'm excited to talk about the DARPA SubT challenge. I think we're interested in that actionable situational awareness. What that really means is, how do you go conduct this underground scavenger hunt and find objects, we call them artifacts, to within a 5-meter global position error. And so here's how this all works.
Here's how to win an event in the DARPA Subterranean Challenge. Find the most artifacts in the shortest amount of time. When, or if, a team's system locates an artifact, it has to report not only the type of artifact, but also its spatially referenced location to an accuracy within 5 meters. A valid report earns 1 point, but teams are granted only a limited number of reports, so they can't just guess until they get lucky. Sound easy enough? Think again. Teams have to send their systems through dynamic terrain, over, under, and around obstacles, in austere navigation conditions, pushing the limits of their endurance, and in conditions degrading sensing capabilities and severely constraining communications. So teams need to be agile, adaptive, and accurate if they want to emerge victorious in the SubT challenge.
So I know many of you are familiar with the SubT challenge. Really excited to have had Team Pluto participate. And I think just to introduce it, we're really interested in understanding these underground environments where at the end of the day, it's too high risk to send people in up front. We're interested in that search and rescue mission, but we have that golden hour or so where before the incident commander sends in rescue personnel, that robots could go in there and identify where hazards are, perhaps even find where those survivors are located, and understand and provide a picture of the lay of the land. So the SubT challenge was constructed in a way that allows for us to explore how not to just be the best runner or best swimmer, but in fact the best triathlete. And that's what we want from our robotic systems here. So we had our tunnel circuit, which is in a coal mine, an urban circuit, which is an unfinished nuclear power plant. Cave circuit, regrettably, was not able to proceed due to COVID. But really the final event, which is coming up in September, is all about how do you put all of those 3 environments together, present that to the teams of robots, and see how well they do. And so this is just a recap, just to calibrate the type of environments that we're talking about when we're talking about SubT.
This is a very exciting experience. So many good teams from all around the world. This is a way to be challenged and to learn things.
Are we up to the task? Can we use our existing technology, our existing expertise?
A lot of the world is going to end up having these fleets of robots. It's very exciting to see all these various and different technologies that are state-of-the-art.
The SubT challenge for us represents everything that relates to how we can make robots to be resilient in extreme conditions.
This is kind of a step up for us, even bigger of a challenge than we faced so far.
It sells to all robotics, make sure that your robots are able to do their mission. This is absolutely difficult at the moment.
So you can see we have a lot of fun with the SubT challenge. As I mentioned, we weren't able to host a systems competition for the cave circuit, but we were able to do a virtual one. Here's just a glimpse of the scenes where you were now sending in virtual robots to go off and find these artifacts as well. And given the Ignition Gazebo simulation environment that DARPA is heavily invested to get to be able to handle these types of complex environments, we're able to study that in a virtual setting right alongside the systems competition. And so speaking to that, the main idea behind this is you set up teams of robots in a staging area. You've never seen this underground course before. You only know that there's one ingress location, and you send them off to go and find the objects that DARPA has deviously scattered throughout this underground setting. And this is mirrored in the virtual setting as well. You're developing algorithms in a software setting, submit your Docker container, you run them against competition worlds that are hidden to you. How well do your robots go and find these types of artifacts and do so in a fixed amount of time? We've been really fortunate, much like what a DARPA challenge is interested in doing, is in exciting and inspiring teams from all around the world to come and join the competition, both on the systems competition where you're building physical teams of robots, as well as the virtual competition where you deploy your software-based solutions. So all around the world, whether it's large research organizations, universities, or even small teams in the age of COVID in your own home workshop, it's an opportunity for new ideas to be captured and brought to bear in a challenge setting. And so I think what's really exciting is September is when our final events will occur. We'll be doing this down at the Louisville Mega Cavern down in Kentucky. We'll co-host the systems and virtual competition at that time. And there's a prize purse of $5 million on the table for competitors to come and show their best and brightest technologies. And there's still time to participate. I'll hit on the dates later for my plug, but we're seeing this march towards this final event, culminating and bringing together all of these technologies, which is pretty exciting. I think, we talked about heterogeneity earlier, but man, when you ask roboticists from all around the world to come up with ways to tackle the underground environment, well, of course, there's going to be a lot of different designs in robotic technologies. So we see that happening, whether it's using the common base platform and building out different sensor and autonomy stacks, or leveraging different custom platforms, or what have you. I think there's just a lot of creativity that's going into these, and each one offers very interesting insights into how and why they're employed in the underground environment. So pretty excited to see any additional teams join the competition before final event and the types of robots that they'll bring. As many of you who have this kind of experience know, it's often the first thing you do is upon arriving at your destination, your hotel, is to find where the Home Depot is, because you know you're going to be needing some extra hardware on site. So kind of getting into some of the technical nuggets, and the things that we at DARPA are thinking about is understanding the insights that we can extract. So here are floor plan pictures of, on the right is the NIOSH mine, the coal mine that we were using for the tunnel circuit, the unfinished nuclear power plant you saw footage of in the urban circuit on the left. You can imagine constructing graphs. You can understand we have reference data sets here that give us insights into the geometry, and understanding, you know, just the notion of scale, the role of distance, the role of topology. You can almost immediately see the tunnel had a lot more closed cycles that might allow for better loop closure, despite the fact that it's a much longer spatial scale to work with. But man, the unfinished nuclear power plant had a lot more nooks and crannies to go and hide, for DARPA to go hide those artifacts, as well as multiple stories that robots had to be able to transcend either through stairs or holes in the wall or holes in the ground. And the virtual environment is no different. In fact, it's way better in the sense that we get to go and explore an even greater complexity and diversity of the types of environments. So this is just showing you the tunnel, urban, and cave virtual worlds that were used, made basically out of Lego brick tiles that you can compose to study different extents of scale or verticality. And we even have a representative cave that was scanned and turned into a mesh for the Ignition Gazebo competition, the SubT virtual testbed. Related to that is this relationship between the systems and the virtual. And so what I'm showing you here are actual robots that were competing in the virtual urban, or sorry, the systems urban competition that have been turned into 3D models that you can use and were used in the virtual cave circuit competition. So these are competitor designed robots that now have and exist in open domain for folks to go and use in their basically fantasy football league style teaming, a construct of a virtual robot team. And you can go and use these robots using that latest and greatest technology from the systems competition in your own virtual competition solution as well. So these are just a few. We have 17 of these robot models that have come from the systems domain, turned into virtual models that you can now go off and use for your approaches as well. So in that vein, I'd say there are numerous ways that the challenge is open to incorporating technology innovations. Whether if you have a new robot, you want to bring that to the table, you can contribute and see how well your robot does when used by the field of competitors. So if you have a robot you'd like to see in the Ignition Gazebo and in the SubT challenge, open submissions are there. I know that there's a lot of work going into modeling sensors for use on robotic systems. So if you have plugins that you want to think about incorporating there, you can build your own worlds for your own simulation purposes using those tiles that we have in our repository, as well as the introductory materials. Basically, if you can walk through these tutorials, you have a solution ready for submission to the virtual competition. I think I wanted to mention quickly that we have a lot of these data products that we've derived from these events, using professional grade equipment to survey and scan down to millimeter precision, a lot of video walkthroughs for those interested in video-based analyses, as well as driving a real robot around to collect data sets with different sensors mounted to them. And I'll say that it's, I wanted to give a shout out to Shreyas and company for their ICRA paper last year on a data set that was really focused on thermal and RGBD motivated by SubT challenge. And that data set actually has been used by a number of other competitor teams. And so it's just really great to see that level of vibrancy across this research community, because that's how we'll continue to push the ball down the field, I think. And so I will highlight this. This is my plug. There are still opportunities for those interested in systems or virtual to be able to compete and register a team. I think if nothing else, following us on YouTube, a lot of fun videos, especially those of teams going and seeing these sites for the very first time, I think is eye-opening. And I always welcome further engagement across the board, just keeping track of what we're doing here. And so finally, I just wanted to throw out there that, as I mentioned, we're really interested in real-world robotics, field robotics in these extreme environments. And it's not just about designing and building the autonomous systems. They are complex, but you know, we really want to work on those systems. But it's not just about the systems, it's how that interacts with the broader mission. What are we trying to accomplish, as well as the environment and the difficulty of those difficult environments that we're operating in. And so here are a smattering of questions, just a few to wet the whistle, but I think we've heard heterogeneity play a role, this idea between understanding when I have one fleet composition and I want to translate to the performance of another fleet's composition. Is there a way to assess and measure that? You know, understanding the role of prior information. If you knew that there were a lot of closed cycles in the environment you're about to maneuver into, will that change your deployment strategy of, do you send in robots that are your comms backbone and set up a network first, and then you send in your scouts? Or maybe you would send in your scouts to generate a map, take advantage of loop closure, and then optimize where your limited comms breadcrumbs might go. So understanding how we could capitalize on that information to change on the fly your deployment and employment strategies, I think is pretty cool. And then, of course, understanding intent of your autonomous system, not just from a human interaction point of view, but also understanding when you don't have direct access to the telemetry feed, what can you learn and understand about what the autonomous system or set of systems is trying to do, and how can that benefit you from a safety point of view, as well as from a security point of view. So I'd be remiss if I didn't leave breadcrumbs for those who are interested in working with DARPA. You can interact with us through these programs or challenges. What I'll propose out here is that oftentimes the ideas for these programs and the next great grand challenge might come from you. And so I really strongly welcome and encourage those types of interactions with myself, as well as other program managers at DARPA, to plant the seed for what might become that new program or next grand challenge. And that's where the seedlings and these exploration ideas come into play. So the answer, the question that you want to answer here is, how do I convince either a program manager or whomever to go from complete disbelief of your concept to, by the time your seedling is done, that the program manager merely doubts success? But you want to go from disbelief to doubt in the purpose of that seedling, and that's to set the stage for that next generation of program ideas. So I definitely welcome that type of engagement. I also wanted to give a shout out for anyone who is becoming a rising faculty or junior faculty. There's the Young Faculty Award, as well as a newly established program in the AI domains for postdocs to receive fellowships as well at DARPA. So I certainly welcome that kind of engagement across the board. And with that, thank you very much, Grass Lab. Always a pleasure, and welcome contact in any shape or form. Thank you.
Thank you, Tim. That was an amazing talk. Always fun to hear about the latest and greatest from DARPA. One thing you might not know is Heilmeyer is a Penn graduate. And we have a Heilmeyer Hall, but now hearing you talk about the catechism, maybe I'm thinking we should put those questions down at the front of the auditorium. So thanks again for doing this. I want to welcome my student co-hosts. So Kelsey Saulnier and Ian Miller, both PhD students in electrical and systems engineering and in the GRASP lab. So Kelsey works in the area of active perception, specifically information-driven mapping strategies for robots. And Ian works on heterogeneous robot systems, semantic mapping and localization across aerial and ground robots. I'm going to turn it over to them. They've been culling questions from the chat sessions and a pre-submitted list of questions through a GRASP form. So Kelsey, Ian, take it away.
Yeah, I guess I'll start. Starting with a question from the audience. So they say at ICRA last year, researchers in multi-robot systems were discussing a lack of robust and consistent performance for even a single non-autonomous robot in unstructured environments. What implications does this have for multi-robot autonomous systems? And what are the important gaps that need to be addressed to bring multi-robot systems to fruition in real applications?
Yeah, fantastic question. And it directly speaks to this notion of needing an appropriate point of departure or a baseline autonomy capability for your individual platforms, because you're basically limited to a large degree by what you can do at the individual level and then how that scales at the multi-robot or swarm levels. So one of the things that we were interested in Offset was seeing how just literally going to sites like Best Buy to go and get the 3DR Solo, or going to small robot vendors and figuring out how to get COTS component-based, commercial off-the-shelf-based robots. That is, the floor, and we wanted to see what we can do with that. And I think what we clearly realized is that you need more capable platforms if you want to elevate the type of tactics that we want to develop. But it goes hand in hand. I wanted to intentionally see how far we could stretch with low-level capability ground robots. And I'll tell you, those air and ground robots, those ground robots will get beached on curbs, which is clearly a problem in urban environments. And so that spoke to this desire to maybe the next program should enhance and focus ground robotics mobility and agility in urban environments, so that you can have the parkour robot that can vault upstairs and open doors and do all of the things that you might need to do in an urban environment. So that's an example, I'd say, of the impact. I wholeheartedly agree that this push towards power up and go type of power on and go robotics is going to be key if we're going to want to get past the notion of debugging robots on start and debugging things like swarm tactics. And so an extensive effort for the Offset testbed platforms has been, how do you get it so, even a firmware update isn't a, isn't a crapshoot and you have to cross fingers before if it's going to work. It's a lot more reliable to be able to do that, yet still incorporating the latest and greatest, dev branch changes. So I think principled software systems and configuration management, logistical support, kind of end-to-end thinking about how to Dockerize nearly everything, if that's the right way to go. Things like that being the foundation for robotic system development might help in some of these areas. And then, of course, is get out in the field and test often, or at least leverage simulation to an accelerated extent to allow for that transfer back and forth more quickly. I do think that that's one of the key limiters right now for multi-robot systems is it's just hard to field multi-robot systems and test them at scale in simulation or in the field. Thanks for the question.
So this is a question that just came in, actually, that I think is good. So the programs you talked about today focus on coordination. Are there any future programs or challenges that focus on more collaboration, where there's more interaction, both physical and strategic, between robots?
Yeah, so I love that question because it speaks to the heart of what makes up for a swarm tactic. And I'd say the ones that I described perhaps are more focused on coordination, but in fact, there is quite a lot of coordination, but a lot of collaboration and cooperation necessary. I'll give you an example. In the Offset scenario, where you're sending in these drones and rovers to go find objects of interest or high value individuals, there are those that have the right sensors or the right simulated effectors to work in that environment. So we have, for example, simulated IEDs, roadside bombs that might take out robots. But if the robots are equipped with a jamming platform, simulated jammer, then they're able to suppress the IED from exploding, and that allows for teammates to go on by. But there's a handoff that needs to occur, recognizing that I am or am not equipped with that capability to handle that task. So that's a little bit of collaboration that's necessary, just as an example. Certainly on the SubT challenge, collaboration is pinnacle for especially, for example, those marsupial platforms where you have ground robots, but they've got drones on top and they get ferried in to be able to handle, for example, the verticality that the ground robots just won't be able to master. So I think there's a lot of advances that not only deal with coordination, absolutely, but the synergies from collaboration and cooperation have really borne out in both offset and SubT. Thanks for the question.
I think I'd like to ask one of the more high-level questions that was put into the chat, and that is, in your opinion, who should be the benefactor of robotics technologies, and what do you envision to be the most important applications of robotics in the coming decades?
Yeah, so I'm going to answer that in a couple of different ways. I'd say the government has historically tried to fund research and be able to inspire cadres of researchers to go off and solve problems of national or international interest. I'd say the amounts of opportunities outside of government funding is immense, and I think that's a great opportunity to go and have broader impacts of robotic technologies in society and community. So I think answering who should be the one patron of robotics research probably is challenging, but I do think that there are places where things like organizations like DARPA have a great opportunity to serve as the lightning rod to maybe drive and create whole new communities, even those that don't have a profit incentive that might drive industry or commercial sectors, and allow for investments that are the 10, 15-year type investments that DARPA is so keenly interested in. So I still see quite the role there. To answer that other question of most important application of robotics, well, I'm going to say everything, of course, because there's a role for robotics in all walks of life. I do think that in safety and security, we will find significantly greater use of autonomous system technologies that implies both a level of maturity, but also a level of responsibility. And we need to continue having the best and brightest focusing on these types of robotic technologies in those applications.
So I'm going to shamelessly exploit my advantage as a panelist to ask you my own question. Have you seen significant differences between the high-level approaches of systems and virtual teams for SubT? And to what extent do you feel like virtual approaches are easily transferred to a systems context?
Yeah, as you're well aware, the kind of reality gap between virtual and physical is very real. And I think the quest to try to bring the gap narrower is both ongoing and going to be increasingly fruitful. I'd say the fun part for both offset and SubT actually has been that we've tried to marry virtual and systems very, very closely. So the software that works in the virtual testbed for offset is the same set of code that is running on robots, just maybe cross-compiled differently. And same goes for the virtual testbed. A lot of the underlying ROS-based nodes, for example, are still running and then just interfacing with the simulator. I think the challenge, of course, is how do you get the particle physics correct for scattering of LiDAR? I'll tell you that's a very real problem because we just released a feature yesterday incorporating scattering in the virtual testbed for SubT, and understanding the sensitivity. So it does boil down to, I think, understanding the derivatives or the gradients of these parameters, not just the point value of how well they work in that setting. And I don't know that we yet know what the derivatives are of that sensitivity or that trade space in both design and also kind of environment and mission parameter spaces. That's just really highly dimensional. So I think to answer your question, the attempt to identify performance metrics that are designed to be mission oriented will allow for a lot of aggregating of performance measures and metrics at the lower levels. So you might be smearing out performance and averaging out how you assess individual pieces. But at the end of the day, we want that measure of effectiveness, as we typically call it, to be measured according to the mission or the capability that you get at the end. So what is the problem you're trying to solve? Find measures that approach that, and then eventually by exploring this trade space or design space or parameter space, we'll be able to start sampling that gradient and then use that as generalizable insights, hopefully. That goes for both sim and real, I would argue.
I think we are past the hour that was allotted to us. Tim, I want to take this opportunity to once again thank you for spending the hour with us. There is a GatherTown link for all of you where Tim will be available to answer other questions. I know I've been looking at the chat questions, a lot of interesting things that we never got a chance to get to. So I hope you'll join us at GatherTown and get a chance to meet Tim virtually, of course, and ask these questions. Thanks again, Tim. Gabby, over to you.
Well, thank you everyone for joining us today. I would like to show you next week's talk actually not next week, March 19th. We'll have Dr. Daniela Russ joining us for the GRASPA Robotics talk. As always, be sure to follow us on social media and to find out about our upcoming events.